Good afternoon, everybody. Very nice to see everybody here at the start of a new series of the Heidelberg Joint Astronomical Colloquium. Just one minor administrative point. I have a list of persons here who have been attending the biscuits and drink session. I'll pass this round, and if you could possibly sign it, please, if you've not already done so, be very grateful. It's just one of those rules of the university, apparently. So on to the science. And we're very glad to start off with radio astronomy this session. And especially we're glad to have Leah Morabito from the University of Durham. And I'd like to pass on to Eduardo, Leah's host, to make the formal introduction.
Thank you very much for coming. It is my pleasure to introduce Professor Leah Morabito from the University of Durham. So Leah started, well, she's from the US and had a US Air Force fellowship to study, which I thought was actually really exciting. We were hearing about this today in my group meeting. If you have time to talk about this tomorrow, she's still in town. So I highly recommend to hear the stories about the US Air Force. Then she, after the fellowship, she decided to continue studying her master's in astrophysics because she was also so fascinated with the radars in the US Air Force that she wanted to continue doing radio astronomy. And then after the master's in Oklahoma, decided to move to Leiden to do a hardcore radio astronomy PhD. That's where she got involved with the LOFAR radio telescope. We'll hear more about this today. And after the PhD, which you finished in 2016, moved as a fellow in Oxford. And after a short postdoc, moved back in 2019 to the University of Durham as a faculty. And since this year, Leah is a full professor. So it's a very impressive CV and a number of awards and fellowships. So I'm very excited to hear all about what LOFAR can tell us about AGN. Take it away.
Thank you. I think I've got one. Yeah, but great. Thank you very much. And it's a great pleasure to be here. I always enjoy talking to LOFAR talking about LOFAR to people, especially when people don't know what LOFAR is. And thanks to Eduardo for, maybe I'll just turn this off and get echoing. Yeah. Okay. And thanks to Eduardo for the very nice introduction. My introduction for myself is usually a bit shorter. I am a radio astronomer, and I like to talk about LOFAR. So if that's all you remember about me today, that's fine. But hopefully you'll remember the content of my talk. So I'll just start with a little bit of an introduction to active galactic nuclei, just for those of you who might study exoplanets or other things and aren't an observational astronomer. So an active galactic nucleus is really at the center of a galaxy. You have at the center, this is an artist's rendition on the left, and on the right, you see the spectral energy distribution. So at the center of this, an active galactic nucleus is when that supermassive black hole is actively feeding on the whatever material is coming in from the galaxy. So it's bringing material in and accreting it. So what does this look like when we observe it with our telescopes? So the first thing that you can see in this picture is there's an accretion disk. This is material that's coming in. It settles into an accretion disk. So if you kind of think about like water trying to go down a drain, it can't all go down at once. And so it ends up with some angular momentum swirling around as it tries to reach that black hole in the center. So as the material comes in closer, it gets crammed together, it gets heated up, very hot. And so it starts to emit in the optical and UV. And I think, Richard, maybe the Zoom needs to be muted here. Are you on Zoom or not? I hear some sort of echo.
Oh, then
I don't know if
let's turn the microphone on.
Yeah.
Right.
Yeah. Okay. Great. Thank you. Okay. So this accretion disk gets very bright and in the optical and UV. Right, okay, yes, okay, so we've just built twice. Right, so then above this accretion disk, you have some hot diffuse gas. This is what we call the corona, and this is emits in the X-ray. And you can see how that contributes to the SED there. Surrounding this region is a dusty torus. So this is literally just dust. We think it's in a torus shape, although there is some debate about this. This dusty torus takes that radiation that's coming off of the accretion disk and it absorbs it, and then you get that re-radiated in the mid-infrared. And so then you have this bump in the mid-infrared that comes from the dusty torus. And then in about 10% of cases, and remember, active galactic nuclei, these supermassive black holes are only active in a few percent of galaxies, but in the population of galaxies where you have an active galactic nuclei, an active galactic nucleus, in about 10% of cases, you end up with relativistic jets. And these we see in the radio. And we'll talk a little bit more about how that radio is generated in a minute. But it's a very small fraction of the overall total galaxies, but you can get a lot of impact from that. So there's two orange lines there for the non-thermal radio and the SED, and we will come back again to why there are two lines on this figure on the right, and discuss why that is. Okay, just to give a little motivation for why we care about AGN. So this is the image on the previous slide, that artist's rendition is the kind of like central tens of parsec in a galaxy. So if a galaxy is really big and you're talking about the central tens of parsec, all of this stuff is going on, why do we actually care about what happens? And the reason is because we think that AGN and galaxies co-evolve. And we see this both from observed relations, like the one on the left here, where you see the supermassive black hole mass, which is plotted versus galaxy velocity dispersion, and you see this very tight correlation, right? So this is not direct evidence, but it is indirect evidence that the galaxies and the AGN at the center are co-evolving. That supermassive black hole knows something about what's happening in the global galaxy, and vice versa. We also know from cosmological simulations that you can take, just a lambda CDM model, but you can't reproduce, for example, the galaxy, the stellar mass function, which you see on the right here. And we know at the low mass end, we know we need stellar feedback. We're not focusing on that today, but at the high mass end, we know we need AGN feedback. So we need that AGN at the center of the galaxy to turn on and do something to be able to reproduce our observations. So this is why we care about AGN. So here's an overview of what I'm going to talk about for the rest of the time. So I'll tell you about radio emission from AGN, a little bit about AGN and radio surveys. We'll talk about the International LOFAR Telescope, and then AGN with LOFAR VLBI. And then I'll finish up with ongoing work and future plans. Okay, starting with radio emission from AGN. There are different types of radio emission. You can have synchrotron emission, which is where you have magnetic fields and free electrons, and those free electrons spiral around the magnetic fields. That spiraling means they're changing direction. Changing direction means acceleration. Acceleration means radiation. So you end up with synchrotron emission is what we call it. At higher frequencies, there's also free or thermal emission from electrons, which are accelerating in just an ionized medium. So there's not really magnetic field lines, but there are ions. And so that impacts the electrons. This is what you might see from a galaxy. This is M82. This is the spectrum there. So you can see the total overall galaxy that's in SED, that's in black. You can see the orange line there, that's the synchrotron emission, and then the thermal line here, which comes in at higher frequencies, and then the dust. For this talk, we're really going to be focusing on synchrotron emission, which can come from several different physical mechanisms, which we'll talk about in just a minute. So we will get to LOFAR, which is the low frequency array, but I want to say a bit about why low radio frequencies are important at this point. So here we see the overall SED of M82, and you can see the synchrotron, but why do we care about going to low frequencies if synchrotron just produces a single power law, right? You just make a measurement at any frequency. If you know the slope of that power law, then it doesn't matter what frequency you're measuring at. So low frequencies are important for several reasons. So first of all, the fact that the synchrotron spectrum is that you have a synchrotron spectrum means that these sources are brighter at low frequencies. So when you're going out and building a telescope, you don't have to build something that is as sensitive as something at higher frequencies. And you're able, or if you do, then you're able to reach a much fainter population at low frequencies, just because things are brighter. It is the only way to measure low frequency absorption. We won't really touch on low frequency absorption in this talk, but just know that you do have processes like synchrotron self-Compton or free absorption, which can impact the low frequency end. And so you cannot measure that with something like the VLA. You have to go to LOFAR frequencies, these really low megahertz frequencies. And then also, it's the only way to probe the lower rest frequencies for high redshift sources. So you can see the spectrum here at z equals 0. You can see that you have to have LOFAR to really understand what's going on with that low frequency turnover. But then if you redshift this to, if you look at a source that's at a redshift 2, right? So first of all, it's fainter to be detected for the VLA, so you need more time on the VLA, but it's still quite bright at low frequencies. And it's the only way you're going to ever be able to capture what's going on at the lower frequencies. So it's important for high redshift sources. And then we'll come back to this later on. I'll show you an example of what I mean by anchoring spectral modeling to assess the spectral age of a source. So if you don't understand that now, that's fine. We'll go into an example. Okay, so what can produce radio emission in AGN? So this is from a nice review by Francesca Panessa in 2019. And these are the 4 different possibilities that she came up with. So we are not going to talk about the Newport effect. So this is where you get radio emission from the corona. This is expected to be negligible for the synchrotron emission that we're talking about today at these low frequencies. So that leaves us with 3 possibilities. The first is jets. So let me explain what I mean by jets. So here are a couple of images of 2 different types of what we call jets. These are Fanneroff-Reilly type source 1 type sources. We have Fanneroff-Reilly type 1, FR1, and Fanneroff-Reilly type 2 sources. So in these sources, you can see at the very, very center, for example, of the FR2, this is the galaxy here. This source on the top here is about 120 kiloparsecs in size. So this is extending far beyond the extent of the optical galaxy. You can see in this FR2, you can see the jets. This is a very nearby famous radio source. This is Cygnus A. You can see the jets. You can see where those jets terminate in what we call hotspots. And then you can see what we call lobes. The source on the bottom looks a little different because although there are jets there that are generated, that are powered by the gravitational potential of the supermassive black hole at the center, they're not as collimated and you kind of end up with this waffly, like diffuse structure. So I will say jets, and I may refer to jetted sources. What I mean is that we think it's one of these types of sources where the morphological features, even if we don't see the jets in the image, if you see something like hotspots and lobes, the way to generate that is with jets. So I may say I will refer to these types of sources as jets or jetted, but that doesn't always necessarily mean that we actually are detecting the jet. We just see morphological evidence that there are jets producing that radio source. The morphology is linked to stellar mass, and there's a very nice paper by Beatriz Mingo if you're interested in taking a look at that. Okay, so that's jets. Another way you could generate radio emission in AGN is shocks from AGN winds. So if you have an AGN wind that's driving out into the interstellar medium and it causes a shock, then you can generate radio emission, synchrotron radio emission from that. And then the final option is star formation. So jets and winds are both AGN driven. Star formation has nothing to do necessarily with the AGN. So we know that radio traces star formation, and what it's actually tracing is the synchrotron emission in supernova remnants. So supernova remnants come from massive stars, which are very short-lived, which means that the radio emission from supernova remnants gives you kind of an almost instantaneous look at the star formation rate. But we see that the radio in star-forming galaxies correlates with the far infrared, which is another tracer for star formation, which is another indication that it is really tracing star formation rate. Okay, so those are the three possibilities. I'll just talk briefly about radio quiet versus radio loud AGN. So coming back to this SED, so radio loudness, or what's plotted here in this, histogram, this value R, this is the ratio between the radio luminosity and the B band's luminosity. And you can see in this paper from 1989, where this was defined, that you have two distributions, right? So you can put a line down, and these correspond to those two lines on the SED plot there. So you can put a line down here at R equals 10 and say, okay, everything to the right of this is radio loud. Everything to the left of this is radio quiet. It's just a simple fraction between the output in the radio and the output at B band, which is thought to be coming from the accretion disk. And that's fine, that's great, nice classification. But then you take an updated radio survey, like first, and all of a sudden you have some issues, right? Okay, so you can see that this is not just two cleanly separated distributions. So you have this kind of like distribution of radio quiet sources and then a long tail of radio loud sources. So the thing is that you can make a cut that is high enough to ensure that you have a clean but incomplete sample of jetted AGN. And that's what this line is showing, right? But anything lower to try to make that sample more complete is just going to be providing you samples that are mixed in terms of what's producing that radio emission. So I'll just mention that radio loud is often shorthand in the community for jetted AGN, but that's really misleading because radio quiet does not mean not jetted, but people often take it to mean that, but that's not necessarily true. And I'll just say it is really unclear what dominates the radio quiet population because there are studies on this, but there's nothing really seriously statistical to look at this in a very wide across the entire population sense. And this is what I'm really interested in and drives a lot of the work that I do. Okay, so if you can't tell from radio loudness, if radio emission is from AGN, can we do it a different way? So let's come back to that radio correlates with star formation information. So here I'm plotting, this is radio luminosity versus star formation rate. And you can see this, so it doesn't matter about, we'll come back to a figure like this later on. But just so you know, the different colors kind of indicate where you have regimes where you're clearly AGN dominated, and this is by definition. So this dashed line that's fitted there is kind of what you can think of as like the main sequence of radio versus star formation for star forming galaxies. And then if you go far enough above that line, then above that, you can be sure that you're dominated by AGN radio emission. And then the converse, right? So again, this below that is we think to be star formation dominated, but how can we be sure? Just like radio loudness, this is maybe a slightly cleaner way to do it, but you still have this problem where in this star formation dominated or radio quiet regime, you can't be sure that that radio emission isn't necessarily coming from all from star formation, and some could be coming from the AGN. Part of the problem is spatial scales. So if we think about, we looked at the nuclear region earlier in this talk, and then you have star formation happens on a galactic disk kind of scales, and then you have galaxy hail up to galaxy cluster scales. So star formation happens kind of on these smaller scales, and potentially AGN winds happen on these smaller scales, although Annalisa would tell you that they extend much further out. But radio jets, we see up to galaxy cluster scales. So these can be up to a few megaparsecs. And our radio surveys, most of our wide area radio surveys, kind of resolve this regime. So we are not getting down to the point where we can tell what's going on with the radio emission because most of our radio surveys don't have the resolution just to probe those spatial scales. Okay, but that's not to say we can't do anything with radio surveys. So let me tell you a little bit about AGN and radio surveys. So radio surveys generally have up to a few arcseconds of resolution. They cover large portions of the sky and a wide range of radio frequencies. So here's just a figure that's trying to compare some of the different, radio surveys out there. You have resolution plotted versus frequency. The color of the points is scaled to the same sensitivity, because if you have a synchrotron power law, right, you can't say that this sensitivity is equal to this sensitivity, but if you take the typical synchrotron spectrum, you can scale everything to one frequency. So these colors give you an indication of how sensitive these surveys are compared to each other. You can see the sky coverage, that's the size of the color in the circle. And then I've just plotted Pan-STARRS and Hubble Space Telescope Wide Field Camera 3 there for comparison to some optical data. So just you may have heard of the faint images of the radio sky at 21 centimeters first. This is kind of like the workhorse radio survey, where if you're not a radio astronomer, this is probably your first stop if you want radio data. So this is at 1.4 gigahertz, 5 arcsecond resolution. And it's been really, really great for the community. There's been a lot of science done with it. But I'm involved in the LOFAR 2-meter sky survey, which is about the same resolution, so 6 arcsecond resolution. But at 150 megahertz, it is actually about an order of magnitude deeper than first. So I would advocate, if you're going to go to somewhere for your first stop for radio information, you should maybe try LOTS first before you try first. Or you can try both. But LOFAR has more sources. We're now up to, I think, 4.4 million sources in our second data release, which only covers about 30% of what we will eventually cover of the northern sky. And there's over 300 science papers already using LOTS data just in the last few years. Okay, so what can we do with LOTS? We can ask the question about, even if we don't have resolution, we can ask the question, do jets extend down to low powers? And so in this paper by a student in 2021, what he did is he modeled total radioluminosity as two components. You can have star formation, and you can have an AGN component. The AGN component was just selected from a simple power law distribution all the way down to low radio powers, and then modeled the entire population. You can't do this on a source-by-source basis. You have to model the entire population. And so doing this, he was able to reproduce the flux density distribution, which you see on the left here. So this is the lines are the models, and the histograms in the background is what's observed. And you could also reproduce the radio loud population. So this is showing stellar mass versus redshift, and the radio loudness fraction is the color. And so this produces, so the models reproduce the radio loud population. Great. So what this means is if you take a look at the simulated population, and that's what you're seeing here on the right, that vertical line is now your canonical radio loudness definition, right? So people who are still using radio loudness would put a line down there and say, everything to the right of this is jets. And then the horizontal line is where you switch from being star formation dominated underneath that line to AGN dominated above that line. And so what you see is that you have this whole population of radio quiet jets. And I say jets here because that's what they said that this AGN model was, but it may or may not be actually jets. It's just radio emission from AGN. And so the question is, how do we identify these to study them? Because these will have an impact on your population, on your galaxy population. They'll have an impact on galaxy evolution. Okay, we can also ask the question, do jets explain everything? So, I mean, if you look at this figure, you can say, yeah, okay, we've got jets all the way down to low powers. Maybe this explains all of the AGN feedback we're seeing, but does that explain everything? So this here is looking at the carbon-4 emission line. So on the right-hand side, you have what we call the carbon-4 emission space. So you have the equivalent width on the y-axis versus the blue shift on the x-axis. And then if you draw kind of this curved line in the space, that's carbon-4 distance. Carbon-4 distance, we think, kind of correlates with the Eddington ratio. So low Eddington ratio is at the top of that gray line, and high Eddington ratio would be at the tip of the arrow. But if you just collapse everything in terms of blue shift and look at the radio detection fraction in blue on the left here, you can see this goes up with carbon-4 blue shift. And you can look at the radio loud fraction in orange, and you can see that starts high and goes down. So what we're seeing here is that we have the jet-dominated, so the radio loud kind of jet-dominated sources on the to the left hand and to the upper left hand parts of these plots. But as you go up in Eddington rate, we think that we switch from jet-dominated to wind and disk-dominated, and we think that's what you're seeing here. That as you go down, as you go up in carbon-4 distance, and this correlates with going up in carbon-4 blue shift, you go down in radio loud fraction, but you go up in your radio detection fraction. So things are no longer radio loud, but you're going up in radio detection fraction. So something else is coming in and causing your radio detection fraction to increase. And we think that is winds based on the carbon-4 emission space work that we've done. So just taking a little bit more of a look at that and looking at connecting disk winds and radio, you can look at broad absorption line quasars. And these are quasars where in the optical spectra, you see broad blue shifted troughs, which implies that there's outflows. So these are AGN outflows, AGN related outflows. It's in about 10% of optical quasars, although there's larger fractions in the radio and infrared. If you're not familiar with what those spectra look like, they look kind of like this, right? So here's your carbon-4 line or whatever, and then here's your broad absorption line. It's blue shifted, it's very deep, very wide. We characterize this by balanicity index, and in 2019, using LOFAR data, I showed that the radio detection fraction of BAL-QSOs is linked to the balanicity index. So the higher your balanicity index, the higher your radio detection fraction. And then my PhD student, well, he's no longer my PhD student, he's moved on to a postdoc in Leiden, followed this up and looked at the optical spectra and found that the radio is linked to the absorption profile. So the radio detection fraction, or the radio detected sources, have a different kind of absorption profile than the non-radio detected sources. That's what you're seeing in the spectra here. And then you follow that up to try to break it down into color, because there's been some work done at Durham showing that a radio detection fraction is also linked to the optical color of quasars, broad absorption line quasars tend to be redder, but it's not entirely explained by color. So even breaking things into the color bins, which is the different colored points, and looking at this carbon-4 distance, you can see that in some of the bins, the broad absorption line quasars, which are the crosses, are still higher than their counterpart diamond, just non-broad absorption line quasars. So it's not entirely explained by color. There's some link that is still there between the broad absorption line quasars and the radio. My other PhD student is also looking at ionized outflows in radio. So she's looked at O3, which I know some people are interested in. And she's found that radio detected in terms of the LOFAR 2-meter sky survey, radio detected sources have more outflows than radio non-detected. And that also, the second component there, when you do fit a second component that is blue shifted, it's a little bit more blue shifted and has a little bit broader. And so that it seems that there is something else going on with the O3 outflow that is perhaps connected to the radio. But again, all of these sources here are star formation dominated, we think, from this radio versus star formation rate plots. None of them are identified clearly as powerful radio jetted AGN. And so we need to be able to figure out what's going on with the radio to try to understand this further. And that's where the International LOFAR Telescope comes in. Okay, so the International LOFAR Telescope, or ILT, is a phased array operating below about 200 megahertz. It's got two bands, the low band and the high band, and these operate just below and above the FM radio band. It's got a very large fractional bandwidth, flexible spectral resolution, a very wide instantaneous field of view. So the instantaneous field of view for the high band antenna is about 20 square degrees. And it has very flexible angular resolution. This is what the antennas actually look like. Here you see the LBA and the HBA. Is not very exciting. When you go out and you look at something like the SuperTurf, which is a collection of 6 stations in the center of the array, I mean, it's just kind of like sticks and grounds with some wires attached to it. Like, it's not very impressive. But what is impressive is that LOFAR has stations spread all across Europe. Although the LOFAR 2-meter sky survey is only processing data using the Dutch stations, which gives it that 6 arcsecond resolution, you can get very flexible angular resolution by including the rest of these antennas. Okay, so what kind of resolution can you get? So with the Dutch stations, which there's 2 different kinds, core and remote, you can get down to about 6 arcseconds at 150 megahertz. And then if you include the International Telescope, you can get to 0.3 arcsecond resolution at 150 megahertz. So all of a sudden, you're beating the ground-based seeing limit. So that's like if you take your best optical telescope with the best adaptive optics that's still on Earth, we can do better at 150 megahertz, which is just really phenomenal. The improvement in resolution going from the Dutch stations to the international stations is about a factor of 20. And so to give you kind of a feeling for what that is, it sounds like a large number, but to give you a kind of feeling, here's an image. Let's pretend this was taken by the Dutch array. You can see there are some shapes, there are some colors, you maybe can't tell what's going on. If I increase the resolution in this image by a factor of 20, then all of a sudden you can see it's my dogs. You can see there are 2 of them, you can see that they're standing on chairs, they're in my backyard, you can see what they're doing. This is the increase in resolution that you get by going from the Dutch stations to the international stations. You can all of a sudden see all of this incredible detail. But of course, there are challenges. And this is what I've spent the last more than a decade of my life working on. Here's a list for you: the ionosphere, data volume, clocks, calibrator, source characteristics. We're not going to go into all of these because that would be an entire another hour-long talk. But I'll just cover a couple things very briefly that I think are key to remember. So the ionosphere is by far our biggest problem. So the reason for this is when we measure information from the sky, we measure this in terms of voltages. We get amplitude and phase of the incoming electromagnetic waves. So we talk a lot about phase because this is what the ionosphere impacts. And so you can see that this is nonlinear with frequency, so it is dispersive, although clock is linear with frequency. So the fact that the telescopes are recording on different clocks introduces this linear error with frequency, whereas the ionosphere introduces this nonlinear behavior with frequency. So clock values are very easy to solve for. We can just model this out of our data, but the phase errors are totally dominated by the ionosphere, and it is a direction-dependent effect, which is much worse at low frequencies, and I'll show you a little video of how that impacts our observations. And then just to say something about source structure, when you go out to these wonderful baselines, you get great resolution, but it makes it harder to calibrate because you have less signal to noise because you have less signal. So this is just for any radio astronomers in the audience, a demonstration of how if you have a point source, your amplitude does not change with your baseline length, but if you have a resolved source, it does, it drops down. You just have less signal on these longer baselines. And so that makes it more difficult to do the calibration that we need to. So I'll just show you this video of what the ionosphere does to our observations. This is not international station observations, but this is the same patch of sky observed on 2 different nights. The field of view here, I think, is about 3 square degrees, 3 by 3, so 9 square degrees. The sources in these images are galaxies. These are distant galaxies. They should not be moving, right? Especially, in terms of these like 30-second frames. But you can see a night on the left with bad ionosphere and a night on the right with good ionosphere. And what the ionosphere does is it causes these galaxies to move in position. They're going up in brightness, they're going down in brightness, they're changing shape. And they're not all doing it in the same way at the same time. So this is what makes LOFAR really difficult and hard to calibrate. This is what we mean by directional dependent calibration, because to correct the galaxy in the bottom of the image, you have to do different corrections than in the top of the image, because they're moving in different ways, because the ionosphere is impacting your observations such that they do different things because you have such a wide field of view. So this is why LOFAR is really, really hard to calibrate. Okay. Oh, I don't want to play it again. I want to go to the next slide. There we go. Okay, so, but we have kind of conquered this. So we can go from something like this. This is an initial calibration of a field. And we can do this directional dependent calibration. I won't, if you want to know all the gory details, you can ask me after. But you can go from that to the image on the right. This is the exact same piece of sky, the exact same data, but now we've implemented directional dependent calibration on the right. And so you can see all the fantastic detail. This is still at a 6 arcsecond resolution image with the Dutch station. Calibrating the international array, we have built on top of that Dutch station calibration. So we go ahead and we calibrate the Dutch station first, and then we use what we call the LOFAR VLBI pipeline. So this is what I've spent a lot of time developing. This corrects for that dispersive delay caused by the ionosphere on the international stations. So some phase calibration. We use some special techniques to help us deal with the data volume and some of the issues that we have with our calibration. And I won't go into that, but you can ask me all about it. And then there are some PhD students who have been working on doing wide field LOFAR VLBI. So the LOFAR VLBI pipeline will give you postage stamp images of things in your field of view. And the wide field will give you a single image of your entire 5.5 square degree field of view at 0.3 arcsecond resolution. But that is very computationally expensive. So there's kind of two different modes. So this is what you get with the LOFAR VLBI pipeline, not this image exactly, but you get postage stamp images of things. This is pretty cheap computationally to do, but then to make a 7 billion pixel image of the entire field of view for one pointing takes a much, much longer, right? So we're talking like at least a couple orders of magnitude longer in time. Okay, so there's kind of different applications. So we'll come back to this at the end, but the LOFAR VLBI pipeline is really nice for like wide area surveys, or if you want to pick something out of lots and just process it at high resolution. And then the wide field LOFAR VLBI mode. VLBI stands for very long baseline interferometry. Sorry, I forgot to define that. The wide field mode is really good for like deep fields where we have lots of ancillary data and we really want to make the most of that. So this is what you get with sub-arcsecond resolution. And this is, you can see part of the poster with the rest of the poster at the top there that advertised the talk. And then it just like a nice little GIF fading from Dutch station resolution out to international station resolution. This is real data from a real field. And this is the improvement in resolution that you get. And you can see this source on the right there is in the top middle there. So it's just really fantastic. And this source looks like a lot like that, those sources I showed you at the beginning, the Fanaroff-Riley sources, which I said were 120 kiloparsecs in size. But this one, you can see, is entirely contained within the optical galaxy itself up there. What else do you get with sub-arcsecond resolution? So I've shown you some results from the LOFAR 2-meter sky survey already, but 90% of the sources are unresolved when you have 6 arcsecond resolution. And so when you go to this higher resolution, you can precisely identify the host galaxy. So as an example here, right, the white circle is what you get with LOTS. And then the red circle there is what you get with using the international stations. So all of a sudden you go from, oh, I don't know which galaxy my radio emission belongs to I can precisely identify which galaxy my radio emission belongs to. And then we can also understand when one source is actually more. So here's an example of a source that in the LOTS catalog, this is one source. It's fit by 3 Gaussians, but we think it looks like a very nice wide angle tail galaxy. But when we do the high resolution image, we see it's actually an FR1, what looks like it's possibly an FR2, and a point source. And just to show you that flexible angular resolution, this is the Elias N1 field, just a single portion of it, but it's been imaged at 6 arcsecond, 1.2 arcsecond, 0.6 arcsecond and 0.3 arcsecond. Because once you've done the calibration for the high resolution imaging, you can go back and you can make images at intermediate resolutions with the telescopes. And so this is from a very recent paper on the Alea Sun 1 field, really, really incredibly beautiful data. Right. Okay, so that's what you get with the International LOFAR Telescope. So I'll just spend a little bit of time on AGN with LOFAR VLBI. So for the high redshift crowd, here's a nice example. We'll come back to that spectral modeling. So this is a galaxy at 2.46, redshift of 2.46, imaged with the HPA by my postdoc Fritz Fein. You can see, again, here's the galaxy at the center, and then these beautiful large structures. So Fritz took this image that he made with the HPA and combined it with an LBA image that I made during my PhD thesis, and then some VLA images at higher frequencies. And he did some spectral modeling to get a spectral age map. So spectral modeling is basically, to get the spectral age, is you start off with a synchrotron spectrum. So over here, this black line is just your power law. But as the radio emitting plasma ages, the higher energy electrons lose energy faster. And so you get this kind of curvature. So the aging happens like this. And this is really the power of LOFAR, because to understand what this initial power law was, you have to go to quite low frequencies to get anywhere close to it. But once you do, then you can say, okay, well, now my curve is this, and I know it was this, so you know how old something is. And you can see that this changes across the source, because at the jet termination point here, you're still getting fresh injection of electrons. And so you're refreshing that population, and it's still quite young. And just to point out, you cannot do this with just the standard resolution of lots. So the Dutch resolution would just say this bottom lobe is just entirely a single source, and you miss out on being able to get any physically meaningful results out of spectral modeling. What I've spent a lot of time on recently is diagnosing AGN activity with high resolution. So basically, very simply, the idea is this. You take models of star formation and you say, okay, my model of star formation predicts an upper limit. Star formation can produce no more than this particular flux density per solid angle, which is proportional to brightness temperature, if you're familiar with that term. So you're basically predicting the surface brightness that your star formation will give you. And anything that is above that will be due to an AGN. So this is traditionally done at gigahertz frequencies with very long baseline interferometry, VLBI instruments, because you need milli-arcsecond resolution. But at low frequencies, at 150 megahertz, you can do this with 0.3 arcsecond resolution. So the idea is, if you make this measurement of your surface brightness of your source with your high resolution image, if it's above this limit for star formation, that radio emission is due to an AGN. And if it's below it, you can't tell if it's due to an AGN or not, but it's likely to be star formation dominated. The nice thing about this is that the only observables you need are the flux density and the size information from the high resolution radio maps. That's it. And you can say whether, if something is above this limit, that it's an AGN. So from there, what you can do is you can separate AGN activity and star formation. So using the 6 arcsecond resolution image, which is gives you your total flux density for the source, if you can identify an AGN in your high resolution image, you can subtract that off, and then you're left with the radio emission from star formation. And so you can do this, and you can take a look at kind of the sources, the fraction of the radio emission that's coming from AGN, and you can see that it's kind of mixed, right? So this is done by different classes, and if you're interested, you can read the paper. But the message here is that really you have composite sources. So even these sources that we thought were just totally dominated by star formation have an average fraction of radio emission coming from AGN of about 0.5, about 50%. Okay, so that's great. And just to show you the real power of LOFAR, this AGN identification using brightness temperature. So on this, you really kind of have to be in the yellow part of this, this color scale to be able to do this. And so the only two things are on this plot that are able to do this is the LOTS HR and the EVN Goods North survey. But this is just showing you why LOTS HR is just like really phenomenal, because this shows resolution and as a function of the number of hours you have to observe 1 square degree, okay? So with LOTS HR, you know, in 8 hours, I can do this. I'm sensitive enough to brightness temperature to do this, sensitive enough to do this AGN identification. But for EVN, you can do this as well, but it takes you, 100 hours to cover the same area as LOFAR, where LOFAR takes much less time. Just to give you a sense, this is that EVN field, the Goods North field, and this is on the left, and on the right is the LASN1 field, and this is an actual 2-scale, relative scale size of the fields. So that Goods North field covers 0.05 square degrees. LASN1 covers 5.1 square degrees. Goods North, you get 31 brightness temperature AGN identifications, and LASN1, you get over 1,500, right? From the same amount of observation time. So this is like one is 32 hours, one is 32.5, but it's just incredible that you can do this. So this is really moving us into the regime of being able to do statistical studies. And so that's what I have this paper submitted looking at doing radioluminosity functions where you've separated the star formation and the AGN. So instead of on the left-hand side here in this left panel, this is radioluminosity functions by galaxy classification. And then on the right, you see by process. So now I've separated that radio emission out into star formation process and AGN process. And then you can compare these. And so if you just divide one of those luminosity functions by the other, so AGN galaxies divide by AGN process, then you end up with this figure, this delta RLF, the difference in the radioluminosity functions on the bottom right. And what you can see here is that we find that there's a contribution of AGN that is 50% more than what's expected for these low luminosity AGN. Above that is the same because those are the really high, easy to identify jetted sources, but we're missing the contribution of these low power, low luminosity AGN. And conversely, we are over predicting the importance of star formation at these radioluminosities. Okay, so in just like the last couple minutes, I'll just finish up with some ongoing work. So we are going back to post-process the LOFAR 2-meter sky survey at high resolution. So this will be LOTS high resolution. So taking this point here and moving it down. So post-processing the data, including the international stations, get to resolution that's comparable to the Hubble Space Telescope. We are only doing postage stamp imaging. So the sky density of sources will not be as high as other surveys, but you will get 0.3 arcsecond resolution, and this will cover the entire northern sky. So you can think about finding rare sources. And this is just showing you how we're going to do it. We're prioritizing the H-Atlas fields, which are here. And these are some postdocs who are working on this with me. And then we'll aim to cover SDSS fields and then start from high declination and go down. We are also continuing to process the deep fields, so working on the Lockman hole, LASN1, NEP, and Booties. And if you're interested in the Cosmos fields, there's also a collaboration with the Cosmos survey where we have some data. It's low declination, so you don't get quite as good resolution, but it's still matched resolution with the VLA at 3 gigahertz. LOFAR itself is going through an upgrade at the moment, so it's not running until the end of kind of 2025. This will upgrade the back-end electronics, which will allow more bandwidth to be used, which gives you more sensitivity for the Dutch stations, which currently only use are capable of only taking data in from half of the dipoles. Or you can split the bandwidth between the HBA and the LBA for simultaneous observations. And so that means we have been limited to very bright sources with the low band antenna, just because the ionosphere is much more difficult to calibrate at the low frequencies. But the idea between simultaneous observations means you can solve for the ionosphere at the HBA and then apply that to the LBA and just solve for the residual effects. So that will be really cool. And then finally, Philip Best and I have proposed for a LOFAR 2.0 large program to look at the Euclid Deep Field North with 3,200 hours to do 0.3 arcsecond resolution imaging over a field of view of about 4 square degrees. And we expect to get sky density of sources of 75,000 per square degree. Okay, right, so I'll just put up my summary because I think I've gone a little bit over time maybe. We've talked about radio emission from AGN and radio surveys, the International LOFAR Telescope, and AGN with LOFAR VLBI, and some ongoing work in future plans. So I'll just leave this up there and say thank you to actually all of the early career researchers who have helped out with LOFAR VLBI over the year, like Pranav, who's sitting right here in the front row, and happy to take questions.
Well, what a mind-blowing collection of data that is. To think 50 years ago, people were so struggling to see anything at all. And I think it's a fantastic thing that you and your colleagues and the whole people associated with this telescope have done. There will be questions from here and also online. I'll start from the auditorium. Please let us know what you want further to know. Yeah. Thank you.
I have a question about star formation and AGN, and I was a bit confused what you meant there. Is it that there is that the probability of an AGN is higher if you have already star formation? Are they correlated?
The probability of an AGN is what? Sorry.
Is that higher if you have star formation? Is that what you meant? Because I wasn't quite sure what you actually. You talked about the separation, yes, and I was wondering whether you can conclude or make any statement about whether they're correlated or whether there's the data shows some correlation, so that there is an enhancement or enhanced probability of star formation when you have an AGN or vice versa. Is that the case, or can you not say anything like this?
So yeah, so in this paper, I did look at this in like kind of the discussion. But so the thing with this is that this is the first time we've really started to do this statistically. And the thing that I would say, I would caution, first of all, is that I think that overall you can say things about populations, but I would not necessarily trust individual sources, like on a source by source basis, because there you can have things like nuclear starbursts, which might mimic AGN, or you might have like diffuse jets, which are AGN emission that are not picked up by brightness temperature. So that's the first thing I will say. So is it more likely that you have AGN when you have higher star formation? So there maybe is correlations, and I do think I plot this in the discussion of that, but that's not really a new result. Is that your question? Am I answering this right? I'm not sure. Okay.
Yeah. Okay. Another question from Keith Durham.
Yeah, it's really awesome. I'm a theorist, and if I think about jets and winds, then for me a wind is just a non-collimated jet.
Yeah. So
you agree with that?
Yeah. I mean, there's huge like discussion in the community. Is it a jet? Is it a wind? Does it even matter? And I think we don't. So I mean, the real question is, does it matter?
Exactly.
And I, as an observer, am not sure. So I do know that there are people who are looking at like how winds might couple differently with the ISM than jets. So Martin Bourne in particular at Hertfordshire is looking at this, but I don't think I'm going to be the one to answer that question. I would love for a theorist to answer that question for me, whether winds and jets couple differently with the ISM, and then I will go out and try to find out where there are winds and where there are jets. But yeah, this is I think especially in particular for radio emission, there's not a lot of simulations where you get predictions for radio emission from the simulations. So there, like Dipanjan Mukherjee's PhD student, Meenakshi, has been doing a little bit of work on this, but there's not a whole lot out there, and I would love more. Great.
Okay, I see there are no questions online. If you do have one, please put your hand up or just type the question in. Yep, Christian Fent has another question.
Hi, thank you. I have a question about the radio loud, radio quiet statistics. You showed this plot, and it was on radio loud, radio quiet statistics. You showed this plot with the upper left corner, and you indicated some radio quiet jets or so. Is that exactly? Yeah.
Yeah.
So are these sources which are radio quiet, but you see jets, you see a structure of jets there? Is or how? I mean, this is only fluxes, yeah.
So this is,
there's no structural information in this.
Right. This is the simulated population, and so all we have here is that the luminosity that's due to AGN or the luminosity that's due to star formation. So the paper assumed that it's star formation and jets, but you could just say it's really just star formation and an AGN component. The thing here is that it is assuming that it's a single AGN component. So just picking from a single AGN distribution of powers, all the way from low to high power. So you can reproduce the radio loud population, which we know are jets from observations, and then the simulation that assumes that that's drawn from the same distribution provides these radio quiet jets here. Does that?
Yes, thank you.
Yeah. I think there was another question in that row there as well.
Thank you. Yeah, so my question was on this decomposition that you have for your total luminosity between star formation rate and AGN. So how do you actually achieve this model-wise? Yes, exactly.
Yeah. Okay. So what you do is so the models here in this figure are from Condon 1992. It's just like, this is the model for star formation that predicts what your surface brightness should be. In terms of, it's a function of frequency. It's also a function of things like redshift, although that doesn't matter as much as you might think. The radio spectral index of the synchrotron spectral index, the electron temperature of the gas, and yeah, that's it. So I've picked a conservative limit here, but basically the models predict what is the maximum surface brightness you can have. And then if you detect something that is above that maximum surface brightness that can be generated by star formation, that has to be due to an AGN. So the thing about this method is that it is, you can make a positive identification of an AGN if you know that it's above the limit of what you can get for star formation. But if something is below that limit, then you can't necessarily say whether or not there's an AGN contribution, because it's entirely possible that it could be due to star formation, but it's also possible there could just be a lower luminosity AGN. Does that answer your...
That answers my question. So in the plot that you had of these different regions, right? Then there was also a certain region in the bottom right of the diagram that are radio loud, but then the star formation rate luminosity sort of dominates.
Okay, so none of these are radio loud. So
yeah, not the one with that you just showed, Christian, for the simulated data points.
Yeah.
Yeah, this one. So you up left, then there's also these little data points in the bottom right or so where there's radio loud, but then they're so but those
so these will not necessarily be picked up by the brightness temperature measurements, because they're not necessarily, because the axis for the brightness temperature you can think of is the y-axis, right? And so it's just being able to make this, it doesn't necessarily translate really well to this plot. but the sources that we're identifying are in this kind of like upper left-hand corner. It may be that if something has a really extreme radioluminosity due to like really massive starbursts, then you might end up picking it up as an AGN. But that's going to be very few sources. I mean, you can see that in the simulated population, there's very few sources in that bottom right. Yeah. Does that answer?
Yeah, no worries. I mean, there's more to ask about, but I'll just catch it later on.
Yes, there'll be plenty of opportunity for discussions. I'll make an announcement in a minute. But just looking, there's nothing online. I just have a very quick question at the end, if I may.
Yeah.
You mentioned, the synchrotron self-absorption, the ability to look at that. Do you see that, especially in the high redshifts?
So we see it, and actually there is a paper. So there's been some spectral modeling done on high redshift sources and some just spectral index maps, which can also indicate where there's low frequency absorption. So there are a couple papers now, but the thing about this is that you only expect the synchrotron self-absorption, for example, in like hotspots, and so you need the resolution, and there's only a handful of papers that have the LOFAR VLBI.
Right. I'm not familiar with the spectral range you have, how long you go, but presumably you at some point you actually pick these up just spectrally, or is it you do need the resolution as well as the spectra?
Yeah.
I mean, obviously, when you've got a hotspot dominating the source, you'll see it in the integrated flux at some low wavelength.
Yes.
Oh.
However, at low frequencies, you are really dominated by the lobe emission.
All right.
And the hotspots contribute only a few percent to the overall total flux.
Okay.
Yeah.
Yeah.
So I mean, like you can see the hotspots in this image, but if you go to the LBA frequencies, which is even lower than this, where you might see more effects from synchrotron self-Compton, there's more lobe emission. So there's more diffuse emission because that's the oldest electron population that's going to be the brightest at low frequencies, whereas the hotspots are the like newest, youngest electron population, and then we'll have a much flatter spectral index. They won't be quite as bright at low frequencies. And so the relative contribution between the lobes and the hotspots is not what you would expect from VLA when you go to LOFAR frequencies.
Really interesting. So if you actually image these regions of self-absorption, presumably you can start to pick out magnetic field and stuff like that from them.
I mean, that's the idea, but we have, again, very few sources. So I think there was this source, and then there was Christina Cordoon, this last reference here, went and looked at another set of these kind of sources. She didn't do spectral modeling for all of them, but she did make some spectral maps.
Right.
So yeah.
All right. Yeah. Well, look, I think we've now run out of time. Before we thank Leah, I'd just like to make a couple of announcements. And I'll put some slides up here. First announcement is next week's colloquium. So we're actually staying with radio astronomy, but we're coming much closer in. So also staying with LOFAR, actually. And we're going to be looking at something really striking, which is radio emission from these aurora and interactions between planets and stars, similar to Io and Jupiter, but with it between a planet and a star. So that's going to be very, very rich in physics, no doubt, and that's something to look forward to next week. Then the last announcement is dinner at 9:30. Please, if you would like to join us, just come down to the front and make yourself known. And Eduardo will then coordinate meeting up at the restaurant. So 7:30 it is, yeah. Okay, right. Thank you. So Leah, thank you again. This is obviously a fantastic field, and I have the impression that it's just on this steep upward curve. So maybe we'll have to invite you back after another few years to actually, you'll actually tell us what really are the final answers of all this. But it's a fantastically rich field, quite obviously. Thank you very much.